So I work on wearable haptic or tactile displays. So these are displays in which you have motors typically and sensors that are mounted in clothing or something in contact with the skin, and you're really trying to see how you can use the skin as a medium of communication. And why we're doing that is there are a lot of environments in which you get a lot of visual feedback, get a lot of auditory feedback, and so you get overloaded and you may not be able to process that information. And so if I start trying to communicate with you using the skin, sort of like people who are visually impaired can use Braille to read, what are your capabilities for doing that? So we do basic work on sort of understanding the motors that we would put on the skin. Think of what's in your mobile devices and sort of have an array of those. We can activate them sequentially in some way, and I can use that to help you navigate an environment that you have no experience with, because now you can say, well, when all those motors go to the left or the right or in another pattern, that means I should go to the left or go to the right and so on. So really extending that concept beyond to a whole range of different sort of situations in which I'd like to be able to communicate with you, because you can't rely on your other senses. So we build displays that have been used by lots of groups. So some of the displays have been used by people who are visually impaired, who have problems in navigation. If you have some way of being able to scan the environment using small cameras, usually people have a GPS on them so you know where they are and you can find out where they want to go, and so you can use these tactile patterns to help them navigate the environments. They've been used for people like firefighters in hazardous environments, again, in which you need to direct them where they should move. And we did some work with the Army, seeing if we could communicate with soldiers, again, in situations in which we needed them to move in certain directions and identify other directions that they shouldn't be moving in. So one big application area is really just trying to offload the sense of vision. So for instance, if you're using your mobile device to navigate, it would be helpful if you didn't walk into traffic by being so fixated on the screen. Can I just have it vibrate in certain ways, directionally, maybe on one side of the display versus the other, and you use that to navigate and only need to look down when there's sort of some specific piece of information that you need. So I see touch as being a much greater component of a lot of consumer electronic devices than it typically is at the moment. Haptics usually has the idea that there's force feedback in the system. So systems that we develop that are a little more in the haptic domain would be ones in which you would use to control robots, maybe in medicine, in particular in surgery, where now you have devices that are outside the body, but the surgeon performing the operation no longer has any mechanical or tactile feedback about what's going on. So you're now trying to see if through the tools that they're holding, can you relay information that tells them where they are in the body in terms of, when tissue is, when a thing like a tumor in an organ, that often feels harder than the healthier tissue around it. In the old days, people could sort of palpate or touch those with a tool. Now they've removed all that sense of touch. And so what you want to do in those applications is really try and restore the sense of touch with a much more improved surgical procedure, but one that's sort of lost some of its capabilities in terms of the human who controls those tools. So some of the challenges sort of generally in haptics are always energy, power, how whatever you add to a device or to a system, it can't be very power hungry. That's not so much a problem with small motors, but sometimes if you have bigger motors that you may want to put in handles and you want it to be portable and movable, then it's really important that people are not constrained by the power required in terms of batteries, systems and so on. And miniaturization, like everything, is an issue as things get smaller. They, certainly in the motor field, they may not generate the signal strength that you want. So for a lot of tactile displays and haptic devices, it's important that the person not have to attend to the information in order to process it. So in other words, I shouldn't have to block out everything else I'm doing in order to feel the tactile input. So it should be robust enough that it directs my attention. Something's coming in, yes, I need to respond to that. So students who have worked with us have gone on to many different areas of research and development in companies and further manufacturing processes associated with consumer products. So some students have gone on to work with Apple and Microsoft. Other students have gone on to companies who work more in sort of consumer medical devices, sort of if you think of Misfit or Fitbit or any of the wearable sensors that people use to monitor exercise. There's a whole sort of growth of applications that you could think of if you start monitoring movements and skin temperature and other things. And then if you've done work in tactile displays, you often have pretty good at doing both the input and output aspect of a system, and that is also something that makes you very appealing to a medical device company, where it's not only that you're sensing things, it's also that the actuation or the input part is equally important in the device that's being developed. You know, like a lot of things, it's always hard to predict what skill set you will exactly need. So what is really important is to develop sort of the basis of learning things in a number of fields. So the students who have worked with me, I'm from a mechanical engineering department, so obviously they have typical mechanical engineering subjects. They've often done courses in electrical engineering to sort of learn basics of electronics. Everyone seems to need to know software these days, and a lot of that has been self-taught because there's not a high level of sophistication needed in some of the applications that we work on. So I think it's just picking up the elements of the systems that you think are really interesting to your own endeavor as a student, and then feeling comfortable when you go to work in a different environment or you go into graduate school that you will be able to master whatever the requirements are there, because you've got the core background that will be the building block for getting those sort of skills in the future. It's important that you get a background that covers, as I was just saying, a little bit of a number of things. So electrical engineering, some mechanical engineering, doing some basic work in biology or systems physiology, neuroscience, so you know a little bit about humans and the sort of how the skin and the senses and the other body parts work, and just making sure you make use of opportunities that you have as an undergrad or an advanced undergrad in terms of any sort of research experiences you can get. And a lot of companies offer internships over the summers that again enable you to explore some of the long-term goals that you may have in terms of where you'd like to work, and see what sorts of interesting things that go on in companies that are really cutting edge in terms of the technologies and devices that they're developing.